Good evening, and welcome to another journey with Sleepy Dreamer. Tonight, as the world around you settles into its quiet rhythm, we're going to explore something extraordinary. A story not of life as we know it, but of something that should have died long ago, yet refuses to fade away. This is the story of a star that said no to the darkness. Before we begin, take a deep breath. Let your shoulders relax and allow your mind to drift toward the edge of wonder. Because tonight, we're traveling to a place where the rules of the universe bend, where time itself slows down, and where something impossibly small holds the memory of something impossibly massive. Imagine for a moment that the universe has a rule book, not written in words, but carved into the very fabric of space and time itself. One of the most important rules in this cosmic guidebook is simple and absolute. All things must end. Stars are born. They shine brilliantly for millions or billions of years. And then, when their fuel runs out, they die. It's as natural as the sun setting each evening, or a candle burning down to its last flicker. The biggest stars, the true giants of the cosmos, those that weigh more than 10 times what our sun weighs, follow an especially dramatic path. Picture a massive bonfire that's been burning for millions of years. Eventually the wood runs out. For a star, the wood is hydrogen, the fuel it burns deep in its core to create light and heat. When that fuel is finally gone, there's nothing left to hold the star up against its own crushing weight. What happens next is spectacular. The star collapses inward, crumpling under its own gravity like a tower of blocks tumbling down. But this isn't a gentle fall. It's violent, catastrophic, and brilliant. The collapse triggers an explosion so powerful that for a few weeks that single dying star can shine as brightly as an entire galaxy of billions of stars. We call this explosion a supernova. After the fireworks fade, what's left should be quiet, cold, silent. The universe expects the remnant to cool down slowly, perhaps fading into a dense, dark lump called a white dwarf, or collapsing entirely into a black hole, a place where even light cannot escape. Either way, the ending should be the same: silence. A gradual fade into cosmic obscurity, like a whisper disappearing into the night. But sometimes, just sometimes, the universe surprises us. Deep in the constellation of Cassiopeia, or perhaps in the ghostly remnants of the Crab Nebula, there is a pulse, a flicker, a heartbeat. It's faint, so incredibly faint that you'd need the most sensitive radio telescopes on Earth to detect it, but it's there, steady, rhythmic, disciplined, a pulse of electromagnetic radiation that crosses impossible distances, travelling for thousands of years through the cold vacuum of space, just to whisper to us, "I am still here." This is not the light of a living star. It's the voice of something that should have gone silent long ago. A star that died once, exploded in fury, and yet somehow continues to exist. Not as a ghost, but as something real, tangible, measurable, something that has refused to accept its fate. The mystery we're unfolding tonight isn't about how this star exploded. That part we understand. The mystery is deeper, stranger, and more beautiful. It's about how, having died once, it continues to draw breath, how it maintains its existence through disciplined rhythmic emission, like a lighthouse keeper who refuses to abandon their post, even after the lighthouse itself has crumbled. This is the story of a star that refused to die. And to understand it, we must first understand what happens when a star's heart stops beating. The star that should have fallen silent. Death and rebirth in the universe. Let's walk through this slowly, step by step, the way we might trace the path of a stream from mountain to ocean. When a massive star finally runs out of fuel, something must give. For millions of years, the star has been engaged in a cosmic tug-of-war. Gravity pulls inward, trying to crush everything down to a single point. But the energy from nuclear fusion in the star's core pushes outward, creating heat and pressure that holds the star up like an invisible scaffold. As long as fusion continues, the star is balanced, stable, alive. But when the fuel runs out, that outward push vanishes. Gravity, which has been waiting patiently all this time, finally wins. The core collapses. Now, imagine trying to squeeze a beach ball into the size of a marble. That's hard, right? But the universe, under extreme gravity, can do something even more extreme. It can squeeze the entire core of a star, something as massive as our sun, down to the size of a city, not a country, not even a large mountain range, a city, about 20 kilometers across. That's roughly the size of Manhattan Island. How is this even possible? Well, atoms, the tiny building blocks of everything around you, are mostly empty space. If an atom were the size of a football stadium, the nucleus at its center would be about the size of a pea sitting at the 50-yard line. The rest is just emptiness, with a few electrons whizzing around the outer edges. Under normal circumstances, atoms keep their distance from each other, their electrons repelling other electrons like magnets with the same poles facing each other. But in the collapsing core of a dying star, gravity becomes so overwhelmingly powerful that it forces atoms together. It doesn't just squeeze them close, it crushes them past the point where they can remain atoms at all. The electrons are forced into the nucleus, where they combine with protons to create neutrons, particles with no electric charge. What you're left with is matter in a state so dense, so compressed, that it resembles the inside of an atomic nucleus itself. This is called a neutron star, and it is, quite simply, one of the most extreme objects in the entire universe. To help you grasp just how dense this is, imagine taking a single sugar cube, one of those tiny white cubes you might drop into your tea. Now imagine that instead of weighing a few grams, that sugar cube weighs as much as 900 Great Pyramids of Giza. That's not a typo. 900 pyramids, each made of millions of tons of stone, all compressed into something you could hold in your hand. That's the density of neutron star material. If you were somehow able to bring a thimbleful of neutron star matter to Earth, it would weigh more than all the humans on the planet combined. The entire mass of 500,000 Earths, squeezed into a sphere only 20 kilometers wide. This extreme compression doesn't just create dense matter, it creates a gravitational field so powerful that it warps the very fabric of space and time around it. Stand on the surface of a neutron star and you'd experience gravity more than 100 billion times stronger than what you feel on Earth. If you tried to escape, you'd need to travel faster than half the speed of light just to break free. Time itself behaves differently near a neutron star. According to Einstein's theory of relativity, powerful gravity slows down the passage of time. For someone standing on the surface of a neutron star, time would pass slightly slower than for someone floating in empty space far away. The neutron star doesn't just exist for a long time. It exists in a pocket of reality where time itself is fundamentally altered, stretched and distorted. This is the physical manifestation of the universe's laws being pushed to their absolute breaking point, a place where the rules that govern our everyday experience, the gentle pull of Earth's gravity, the steady tick of clocks, the empty space between atoms, are momentarily overruled by something far more extreme. This is not a choice. It's a violent mandate imposed by the mechanics of space-time itself. The star has no say in the matter. It is forced by the sheer weight of its own existence into this new, impossibly dense state. The neutron star is held together not by hope or will, but by neutron degeneracy pressure and the repulsive nuclear forces that prevent neutrons from being crushed any further. It's a standoff between gravity, which wants to collapse everything into a black hole, and quantum mechanics, which says, no further. And so the star endures, not because it wants to, but because the laws of physics give it no other choice. It has died, yes, but in dying, it has been reborn into something stranger, denser, and more enduring than anything that came before. The collapsed core now sits in the center of an expanding cloud of debris, the outer layers of the star that were blown away in the supernova explosion. That cloud glows with the memory of the explosion, illuminated by the energy still radiating from the hot, young neutron star at its heart. To an observer, thousands of light years away, this remnant looks like a nebula, a beautiful, glowing cloud of gas and dust. Hidden at its center, barely visible, is the tiny, dense heartbeat, the pulsar. And that pulse, that rhythmic flash of light, is the star's declaration. I am still here. I've not gone quietly. I refuse to be silent. This is where our story truly begins, with a star that should have fallen silent, but instead chose to shout across the void. A star that, against all odds, continues to assert its existence, one pulse at a time, across the vast and patient darkness of space. And as you drift towards sleep tonight, let this thought settle gently into your mind. Even in death, some things refuse to fade. Some things, through sheer persistence and the strange, beautiful laws of physics, continue to shine long after their light should have gone out. The universe hums with these quiet acts of defiance, and tonight we've just begun to listen. As you settle deeper into your pillow tonight, let's continue our journey through the darkness. In part 1, we discovered a star that refused to die, a collapsed remnant that defied the universe's expectation of silence. We learned how massive stars collapse into impossibly dense neutron stars, squeezing the mass of 500,000 Earths into a sphere the size of a city. But we left one question unanswered, hanging in the cosmic void like a distant lighthouse beam cutting through fog. What exactly is making that pulse, that rhythmic heartbeat echoing across thousands of light years? Tonight, we'll discover the ghost in the machine, the mechanical marvel that transforms a dead star's last reserves of energy into a voice that spans millennia. Take another slow breath. Let the weight of the day drift away. Because we're about to meet one of the universe's most famous ghosts, a star whose death was witnessed by our ancestors nearly 1,000 years ago, yet continues to speak to us every night. Our story now turns to a specific star, one with a name humans gave it long before they understood what it truly was. We call it the Crab Pulsar, though its scientific designation is PSRB 0531+21. It lives inside a beautiful glowing cloud called the Crab Nebula, also known as Messier 1, the first entry in the famous catalogue of fuzzy objects that confused early astronomers searching for comets. But this star's story begins much earlier, on a summer morning in the year 1054. Imagine yourself as a Chinese astronomer, standing in the cool pre-dawn darkness, carefully recording the positions of the stars as your colleagues have done for centuries. Suddenly, without warning, a new star appears in the sky, not gradually, but instantly, as if someone had flipped a cosmic light switch. This guest star, as the Chinese astronomers called it, blazed so brilliantly that it was visible even during the daytime, competing with the sun itself for attention. For 8 consecutive months, this mysterious visitor remained visible in the night sky, slowly fading like a dying ember. Astronomers across the world, from China to Japan to the Islamic world, documented this extraordinary event in their records. They had no way of knowing they were witnessing one of nature's most violent events, a supernova explosion, the catastrophic death of a massive star. The star they watched exploding was located about 6,500 light-years away from Earth. Think about that distance for a moment. Light, which travels faster than anything else in the universe, racing at 300,000 kilometers every single second, took 6,500 years to reach our planet. The explosion those medieval astronomers witnessed had actually occurred around the time early humans were just beginning to develop agriculture, long before the pyramids were built. And here's the beautiful part. The light is still arriving. Right now, tonight, photons from that explosion are still streaming past Earth, carrying the memory of that violent moment across the vast gulf of space and time. In 1968, more than 9 centuries after the supernova, astronomers made an extraordinary discovery. Using radio telescopes, they detected rapid, precise pulses of radiation coming from the center of the Crab Nebula, the glowing cloud of debris left behind by the 1054 explosion. The pulses arrived with stunning regularity, over 30 times per second. Tick, 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 faster than your heart beats, more reliable than any human-made clock. They had found the ghost, the collapsed core of the star that exploded in 1054, still spinning, still radiating, still very much alive in its own strange way. This discovery was profound. It confirmed a bold prediction that had been made years earlier, that neutron stars, those impossibly dense remnants we discussed in Part 1, should exist at the centers of supernova remnants. The Crab Pulsar provided the proof. Here was a star that humanity had watched die nearly 1,000 years ago, and yet we were now detecting its heartbeat, steady and strong. The Crab Pulsar isn't just shouting across space, it's shouting across time. The light beam we detect today is a 6,500-year-old signal, like receiving a letter that took millennia to arrive. When that light began its journey, humans on Earth were hunter-gatherers. By the time it reaches your eyes, looking through a telescope, civilizations have risen and fallen, languages have been born and forgotten, and our entire understanding of the universe has transformed. But how does this ghost speak? What creates that precise, rhythmic pulse? The answer lies in one of nature's most elegant mechanisms, a cosmic lighthouse. Picture a lighthouse standing on a rocky shore, its powerful beam cutting through the fog. As the light rotates, it sweeps across the dark ocean. A ship far out at sea doesn't see the light constantly. It sees regular flashes as the beam points toward it, then away, then toward it again. Flash, darkness, flash, darkness, flash. The Crab Pulsar works exactly the same way, but instead of a beam of visible light sweeping across an ocean, it's a beam of electromagnetic radiation sweeping across space. And it does this more than 30 times every second. But what creates the beam? Why does this tiny collapsed star, only 20 kilometers wide, behave like a lighthouse at all? The answer involves 2 key ingredients: extreme rotation and an unimaginably powerful magnetic field. When the massive parent star collapsed to form the neutron star, something remarkable happened. The star was spinning slowly before the collapse, perhaps taking weeks or months to complete a single rotation. But as it shrank, getting smaller and smaller, it spun faster and faster, like an ice skater pulling in their arms during a spin. This is called conservation of angular momentum, one of the fundamental laws of physics. The same principle that makes a spinning figure skater rotate faster when they pull their arms in close to their body caused the collapsing star to spin up to incredible speeds. By the time it finished collapsing into a neutron star, it was rotating over 30 times per second. Imagine that. An object containing more mass than our Sun, compressed into something the size of Manhattan, spinning 30 times faster than a ceiling fan. The surface of the neutron star is moving at a significant fraction of the speed of light. Nothing we experience in daily life can compare to this kind of rotation. But rotation alone doesn't create the pulse. The second ingredient is the magnetic field. The parent star had a magnetic field, like Earth does, but nothing extraordinary. However, when the star collapsed, that magnetic field got compressed, along with everything else. Just as the density increased by trillions of times, the magnetic field strength increased proportionally. The result is a magnetic field about 1 trillion times stronger than Earth's, one of the most powerful magnetic environments in the universe. This magnetic field has poles, just like the magnets you might stick on a refrigerator, a North Pole and a South Pole. But here's the crucial detail. The magnetic poles don't align with the rotation axis of the star. They're tilted, offset, pointing in a slightly different direction. This misalignment is essential. The powerful magnetic field channels streams of high-energy particles, electrons and other charged particles, which pour out from the magnetic poles at tremendous speeds. These particles, racing along the magnetic field lines, emit intense electromagnetic radiation, everything from radio waves to X-rays and even gamma rays. Because the magnetic poles are tilted relative to the rotation axis as the neutron star spins, these beams of radiation sweep through space like searchlights. If Earth happens to lie in the path of one of those beams, we see a pulse of light, flash. Then, as the beam rotates away from us, darkness. Then, as it comes around again, another flash. 30 times a second, the Crab Pulsar's beam sweeps past Earth, and 30 times a second, our telescopes detect that rhythmic signal. The star isn't turning on and off. It's constantly emitting radiation from its poles. We simply see it only when the beam points our way, like seeing a lighthouse only when its beam sweeps across your position. The precision of this pulse is breathtaking. Some pulsars, particularly the older ones that have been spinning for millions of years, keep time more accurately than the best atomic clocks humans have ever built. When astronomers first discovered pulsars in the 1960s, the signals were so regular, so precise, that some scientists briefly wondered if they might be artificial, signals from an alien civilization. They jokingly called the first pulsar discovered LGM-1, standing for Little Green Men. Of course, nature turned out to be far more interesting than fiction. These weren't alien broadcasts, they were the universe's natural clocks, massive cosmic metronomes ticking away in the darkness. When scientists convert the electromagnetic pulses into sound waves, something magical happens. The rapid ticking becomes an audible rhythm, a sound that's been described as resembling an overactive bumblebee, a rapid thumping or humming that's both mechanical and strangely organic. It's the star's voice, its declaration of existence. I am still here. I am still here. I am still here. This is the pulse of memory. With each rotation, each flash, the neutron star reminds us that it exists, that it survived its violent death, that it refuses to fade quietly into the cosmic background. It's a monument of persistence, not built from stone or metal, but from the fundamental forces of nature itself. But this remarkable performance doesn't come without cost. The Crab Pulsar, like all isolated pulsars, is slowly winding down. Each pulse, each burst of radiation requires energy. That energy comes from the star's rotation. With every flash of light, the neutron star spins just a tiny bit slower. It's losing rotational energy, bleeding it away into space through magnetic radiation and the acceleration of particles. This slowdown is incredibly gradual. The Crab Pulsar's rotation period increases by about 38 nanoseconds per day, a change so tiny it would take decades to measure without precise instruments. But it's happening. The star is aging, slowly but inevitably. Yet every so often, something extraordinary interrupts this steady decline. The star experiences what astronomers call a glitch, a sudden sharp increase in rotation speed. Since 1968, when scientists began monitoring the Crab Pulsar closely, it has experienced 24 such glitches. 24 moments when the star briefly rebelled against its fate, spinning faster instead of slower. What causes these glitches? Scientists believe they originate deep inside the neutron star, in a region where neutrons exist in a bizarre quantum state called a superfluid. In this state, the neutrons flow without friction, spinning faster than the solid outer crust of the star. Normally, these two regions, the superfluid interior and the solid crust, rotate somewhat independently, but occasionally the two couple together. The rapidly spinning interior suddenly connects with the crust, transferring angular momentum and causing the whole star to spin faster for a brief period. It's like a gear suddenly catching, momentarily reversing the slowdown. These glitches are the star's internal rebellion, a physical manifestation of its refusal to go quietly. Even as it ages, even as its rotation gradually decreases, it fights back with sporadic bursts of renewed vigor. The persistence we observe isn't passive survival, it's active, dramatic resistance. The Crab Pulsar is relatively young by cosmic standards. At just 971 years old, counting from when the supernova occurred in 1054, it's practically a newborn compared to some pulsars that are millions of years old. Its rapid rotation, 30 times per second, and its powerful magnetic field mark it as energetic and youthful. As you drift towards sleep tonight, consider this. Somewhere in the constellation Taurus, visible from Earth on winter nights, a tiny sphere only 20 kilometers wide is spinning at unimaginable speeds. Every 33 milliseconds, its beam of radiation sweeps past our planet, a cosmic reminder that has been ticking away for nearly a millennium. Medieval astronomers watched its birth and recorded it in their chronicles. Modern astronomers listen to its voice and decipher its message. And every night, whether we're watching or not, it continues its patient broadcast, a ghost in the machine, a star that refused to die, speaking across the void in the only language it knows, the rhythmic pulse of persistence. The universe hums with countless such voices, neutron stars scattered throughout the galaxies, each one a testament to nature's ability to transform death into something strange, beautiful, and enduring. The Crab Pulsar is just one we happen to know well, one whose story intersects with our own human history in a way that reminds us how small we are, and yet how lucky to witness such wonders. Rest now, knowing that the cosmos is alive with these quiet, persistent rhythms, and tomorrow, when you wake, that distant star will still be spinning, still pulsing, still refusing to be forgotten. There's a law in physics, one of the most fundamental and inescapable rules in all of nature. It's called the second law of thermodynamics, and in simple terms, it states that everything in the universe tends toward disorder. Heat flows from hot objects to cold ones, never the reverse. A sandcastle on the beach gradually crumbles. A hot cup of tea slowly cools to room temperature. Stars burn their fuel and eventually fade. This law describes something called entropy, a measure of disorder or randomness in a system. The second law tells us that entropy always increases over time. The universe, in its entirety, is slowly moving from a state of order to a state of disorder. It's like a grand cosmic wind-down, where all the organized structures, all the complex patterns, eventually smooth out into uniformity. In a way, this law is about loneliness. It tells us that everything isolated, everything cut off from new energy sources, must eventually grow cold, still, and silent. Stars die, planets cool. Even black holes, the most persistent objects we know of, are predicted to eventually evaporate over incomprehensibly long timescales. Against this backdrop, the pulsar appears as something remarkable, almost defiant. Here is an object that has already died once. It no longer generates new energy through nuclear fusion, the process that kept it alive for millions of years. It has no fuel left to burn, no reserves to draw upon. By all accounts, it should be cooling down, fading away, succumbing to entropy's gentle but inexorable pull, and yet, there it spins, radiating, pulsing, broadcasting its existence across thousands of light years, maintaining an immense structured magnetic field, keeping perfect time with its rotation, existing as a monument of order in the cold vacuum of space. How can this be? How does a dead star defy the universe's most fundamental law? The answer is both simple and profound. It doesn't defy the law. It obeys it, but on such a vast time scale that the decay appears, from our brief human perspective, to stretch toward infinity. The pulsar's fuel is not nuclear energy anymore. Its fuel is motion, specifically rotational energy. When the parent star collapsed, it transferred almost all of its gravitational potential energy into the rotation of the resulting neutron star. Think of it like winding up a cosmic spring, storing an enormous amount of energy in the form of spin. The neutron star is now spending that stored energy, very, very slowly. With each pulse of radiation it emits, with each particle it accelerates along its magnetic field lines, it loses a tiny amount of rotational energy. The star spins just a little bit slower. Over decades, over centuries, over millennia, this slowdown continues. But here's what makes it so extraordinary. The amount of energy stored in that rotation is vast beyond comprehension, and the rate at which it's being released is incredibly steady. The Crab Pulsar, for instance, is losing rotational energy at a rate of about 5 times 10 to the 31st power watts, which is about 100,000 times the total power output of our Sun. That sounds like a lot, and it is, but the neutron star has so much rotational energy to begin with that it can sustain this output for thousands, even millions of years. The pulsar isn't defying entropy. It's executing the law with such staggering patience that it transforms physical decay into something that appears, from our perspective, almost eternal. Let me give you a way to picture this. Imagine you have a massive flywheel, so heavy and so perfectly balanced that once you get it spinning, it continues for an incredibly long time, even though friction is slowly draining its energy. The Crab Pulsar is like a flywheel with more mass than the Sun, compressed into a space the size of a city, spinning 30 times per second in the near-perfect vacuum of space where there's almost no friction to slow it down. It's the universe's most perfect spinning top, wound up by the violence of a supernova and now spinning down over geological timescales. And here's another layer to this story, one that adds a beautiful philosophical dimension. The light we observe from the Crab Pulsar began its journey 6,500 years ago, when ancient humans were just discovering agriculture, when they were painting on cave walls and telling stories around fires. Photons of light were leaving the pulsar and beginning their long journey through space. Those photons have been travelling ever since, crossing vast stretches of emptiness for 65 centuries. The light carries memory. It carries the indelible imprint of the star's death and its mechanical rebirth. Each photon is a messenger, a physical manifestation of an event that happened in the deep past, now arriving at our doorstep like a letter that took millennia to deliver. When you observe the pulsar through a telescope, you're not just seeing light, you're seeing time itself, stretched out across the cosmos. For the pulsar, sitting in its profound gravitational well where time passes differently than it does in empty space, the subjective experience of time is altered. Einstein's theory of general relativity tells us that powerful gravity slows down time. For an observer standing on the surface of the neutron star, assuming they could somehow survive the experience, time would pass slightly slower than it would for someone floating far away in empty space. This means the pulsar exists not just for a long time, but in a region of space-time where the passage of time is fundamentally different. It doesn't simply endure, it endures in a pocket of reality where the universe's clock ticks at a different rate. This technical reality lends a deeper meaning to the observation that the pulsar seems to exist outside normal time. So what is the secret? How does this star, stripped of its nuclear furnace, continue to glow across the aeons? The answer lies in efficiency, a quality that nature sometimes achieves with breathtaking elegance. The pulsar generates no new heat. Unlike the Sun, which fuses hydrogen into helium in its core and produces vast amounts of thermal energy, the neutron star is cooling down. When it first formed in the supernova explosion, the neutron star's interior was heated to temperatures of billions of degrees. But with no fusion reactions to maintain that heat, it began to cool immediately, radiating energy away as neutrinos and photons. Over the centuries since its birth, the Crab Pulsar's surface temperature has dropped from millions of Kelvin to perhaps a few million Kelvin today. It will continue to cool over millions of years, eventually becoming a cold, dark remnant. But that cooling process is separate from the pulse we observe. The pulse, the lighthouse beam, doesn't come from heat, it comes from motion. The pulsar's true fuel is its angular momentum, the rotational energy stored in its spin. And the mechanism that converts this rotation into light is magnificently efficient: magnetic dipole radiation. Imagine the neutron star as a giant magnet spinning in space. The magnetic field, anchored to the star, spins along with it. But magnetic fields can't spin faster than the speed of light. There's a distance from the neutron star, called the light cylinder, where the rotation would require the magnetic field to move at light speed. Beyond that distance, the field lines can't keep up. This creates a zone of tremendous electromagnetic stress. Charged particles, electrons and positrons, are plucked from the neutron star's surface and accelerated to incredible energies along the magnetic field lines. As these particles spiral and accelerate, they emit electromagnetic radiation, radio waves, light, X-rays, even gamma rays, beaming out from the magnetic poles. This process is incredibly efficient at converting rotational energy into electromagnetic radiation, and because the neutron star has such enormous angular momentum to begin with, the process can continue for a very, very long time. But the star's power doesn't just radiate into empty space, it actively shapes its environment. The pulsar sits at the centre of the Crab Nebula, the expanding cloud of debris from the 1054 supernova. The nebula glows, illuminated not by reflected starlight, but by the energy pouring out of the pulsar itself. The high-speed particles and intense radiation from the neutron star create what's called a pulsar wind nebula, a dynamic structure where the star's output collides with the surrounding gas, heating it, ionizing it, making it glow. This is the star's power made visible. It's not content to pulse quietly in the darkness. It reshapes the space around it, pushing back against the void, inscribing its existence onto the very geometry of the surrounding nebula. The star's voice isn't just audible in radio receivers, it's physically written into the structure of the cosmos around it. Scientists have developed mathematical models to describe how pulsars slow down over time. The simplest model, called the magnetic dipole model, predicts that the rate of slowdown should follow a specific pattern, described by something called the breaking index. For a perfect magnetic dipole, this index should equal 3. But when astronomers measure real pulsars, they often find slightly different values, indices closer to 2.5 or 2.8. This small discrepancy is fascinating because it suggests that the energy loss isn't perfectly described by magnetic dipole radiation alone. Other factors might be at play: stellar winds carrying away particles, subtle changes in the magnetic field over time, or even oscillations in the neutron star's shape. This slight deviation from the most rigid theoretical prediction is beautiful in its own way. It suggests that the universe allows for a degree of complexity, a softness in its mechanisms that permits these monuments of persistence to last a little longer than the strictest models predict. The pulsar's duration appears prolonged beyond perfect theoretical expectations, a sign that reality is richer than our simplest equations. As the Crab Pulsar ages, as it continues to spin down over the coming millennia, it will eventually reach a point where its rotation becomes too slow, or its magnetic field too weak, to generate the powerful beams we observe. When that happens, perhaps millions of years from now, it will cease to be a pulsar. It won't explode again, it will simply go quiet, becoming one of countless silent neutron stars scattered throughout the galaxy, cooling remnants that no longer announce their presence. But until that distant day arrives, the Crab Pulsar, and thousands of others like it scattered across the Milky Way, continue their patient broadcast. They are the universe's timekeepers, its metronomes, its stubborn witnesses to the principle that even in death structure can persist. They remind us that the laws of physics, while absolute, can produce outcomes of astonishing duration. That entropy, though inevitable, can be resisted for cosmological timescales through the simple but profound mechanism of stored energy being released with exquisite slowness. The pulsar doesn't defeat entropy, it dances with it, spinning through space in a performance that lasts for aeons, a testament to nature's ability to create beauty and persistence, even in the aftermath of catastrophic violence. As you drift towards sleep tonight, consider that somewhere above you, invisible to your eyes but detectable by our instruments, countless pulsars are spinning. Each one is a clock, a monument, a voice speaking across the void. Each one was once a massive star that lived, died, and was reborn into something strange and enduring. The universe is filled with these quiet acts of defiance, these demonstrations that persistence isn't about refusing to change, but about changing so slowly, so gracefully that the transition from life to death stretches across millions of years and becomes, in its own way, a form of immortality. Rest now, knowing that the cosmos continues its slow, patient unfolding. The pulsars will still be spinning when you wake, and long after we're gone, they'll continue their broadcasts, lighthouse beams sweeping through the darkness, reminding no one in particular that they are still here, still enduring, still refusing to be forgotten. The star that refused to die isn't fighting against the universe. It's simply taking the universe's rules and stretching them across such vast expanses of time that the result looks like magic, feels like defiance, and sounds like a heartbeat that will echo for millennia to come. And so we arrive at the final chapter of our journey, dear traveller. Your breathing has grown steady, your mind has wandered through the birth and persistence of neutron stars, and now we must face what all things must eventually face, the end. But as you'll discover in these closing moments before sleep claims you completely, endings in the universe are rarely final. They're transformations, quiet transitions from one state to another, like the gradual shift from twilight to darkness, or from wakefulness into dreams. In parts 1, 2, and 3, we followed the story of a star that refused to die. We watched it collapse from a massive giant into a city-sized sphere of impossible density. We listened to its pulse, that rhythmic heartbeat broadcasting across 6,500 light-years of space. We explored how it defies entropy, not by breaking the rules, but by executing them with such patience that its decline stretches across millions of years. But now, as all stories must, we come to the long goodbye. Let your eyes close gently if they wish. The universe will continue its patient work whether we're watching or not. Nothing lasts forever. Not stars, not galaxies, not even the universe itself, at least not in its current form. The second law of thermodynamics, that fundamental principle we explored in part 3, always has the final word. Energy spreads out. Order gives way to disorder. Hot things cool down. Spinning things slow down. and eventually even the most persistent pulsars must fall silent. The Crab Pulsar, our companion throughout this story, is still young at just 971 years old. It spins rapidly, 30 times per second, and radiates powerfully across the electromagnetic spectrum. But it won't always be this way. With every rotation, with every pulse of light it sends into the void, the pulsar loses a tiny amount of energy. Its rotation slows down by about 38 nanoseconds each day, a change so small that you'd never notice it without precise instruments. But time is patient, and those nanoseconds accumulate. Over thousands of years, those accumulated nanoseconds will become microseconds. Over millions of years, they'll become seconds. The pulse frequency will drop from 30 times per second to 20 times, then 10, then 5, then 1. Eventually, the rotation will slow to the point where the pulsar can no longer generate its powerful beams efficiently. The lighthouse will begin to flicker, its beam growing weaker and more sporadic. But there's another factor at play. The magnetic field itself is decaying. When the neutron star first formed, its magnetic field was locked into the structure of the star, frozen into the crust like iron patterns in ancient rock. But magnetic fields stored in conductive material don't last forever. They slowly dissipate through a process called ohmic decay, where the magnetic energy is converted into heat through electrical resistance in the crust. Scientists estimate that the magnetic field of a neutron star decays with a timescale of several million years. For the Crab Pulsar, which is less than 1,000 years old, the field is still strong, about 7.6 trillion times stronger than Earth's magnetic field, but in a few million years, that field will have weakened considerably. As the magnetic field decays and the rotation slows, the two processes work together to gradually shut down the pulsar mechanism. The beams become less focused, the particles accelerated along the field lines have less energy, the pulse grows fainter, harder to detect until finally it can no longer be observed at all. This isn't a sudden death. There's no second explosion, no dramatic finale. It's a gentle fade, like a voice growing quieter and quieter until it merges with the background silence. The neutron star doesn't disappear. It simply stops being a pulsar and joins the vast population of silent neutron stars scattered throughout the galaxy. Imagine walking through a dense forest at twilight. Some of the trees are illuminated by the last rays of the setting sun, glowing golden and visible for miles. But most of the trees stand in shadow, dark and unnoticed. The galaxy is like that forest. For every pulsar we can detect, glowing brightly in radio waves, there are likely dozens of silent neutron stars, cold remnants that spun down long ago and now drift invisibly through space. The neutron star itself continues to exist, of course. It's still incredibly dense, still warping space-time around it with its powerful gravity. But it's no longer hot enough to glow brightly, and it's no longer spinning fast enough or maintaining a strong enough magnetic field to power the pulsar mechanism. In its final state, the neutron star becomes something like a cosmic fossil. It was born in the violence of a supernova. It lived a brief but brilliant life as a pulsar, and now it enters a long, quiet retirement. Its surface temperature, once millions of degrees Kelvin, slowly drops over tens of millions of years. Eventually it will cool to just a few thousand degrees, then less, fading like an ember in a dying fire. In this cold, dark state, the neutron star resembles what scientists sometimes call a black dwarf, though that term technically refers to a different type of stellar remnant. But the comparison is apt. Both are the cold, faint endpoints of stellar evolution, objects that have exhausted all their usable energy and now simply exist, cooling slowly toward the background temperature of the universe itself. This fate isn't defeat, it's acceptance. It's the natural conclusion to a process that began with a star's violent death and continued through millions of years of gradual energy release. The pulsar didn't fail, It completed its task. It took the tremendous energy stored in its rotation and magnetic field and broadcast it across the cosmos, illuminating its corner of the galaxy, shaping the nebula around it, and providing scientists with a natural laboratory to study extreme physics. And when its work is done, it rests. But this isn't quite the end of the story, because in the universe, endings are also beginnings. Remember that the massive star that created our neutron star spent millions of years fusing lighter elements into heavier ones. In its core, hydrogen became helium. Helium became carbon and oxygen. Those became neon and magnesium, and so on up the periodic table, all the way to iron. The star was a cosmic forge, creating the chemical elements that make up planets, oceans, and even our bodies. But iron is as far as normal stellar fusion can go. Creating elements heavier than iron requires even more extreme conditions, more energy than normal stars can provide. For decades, scientists wondered where elements like gold, platinum, silver, and uranium came from. The answer, they discovered, lies in events involving neutron stars. When two neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves that ripple through space-time itself. Eventually, they collide and merge in one of the most violent events in the universe, an explosion that, for a brief moment, rivals the brightness of an entire galaxy. In that collision, in the intense heat and pressure of neutron-rich matter being torn apart and reassembled, the heaviest elements in the periodic table are forged. Gold, platinum, uranium, all the elements heavier than iron that exist in the universe were created in these neutron star mergers and scattered into space. So the neutron star, even in its silent state, carries within its structure the seeds of future worlds. Its matter, some of the densest material in existence, is destined to eventually be recycled back into the cosmic ecosystem, either through collision and merger or through other processes we're still discovering. The star's legacy isn't just the light it emitted or the time it kept. Its legacy is physical, material, written into the atoms that will one day form new stars, new planets, perhaps even new life. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in stars. And the gold in jewelry, the platinum in electronics, the uranium in the Earth's core, those came from neutron star collisions. The pulsar's defiance, its millions of years of persistence, ensures that its matter remains in a useful form, concentrated and rich in exotic nuclear configurations, ready to contribute to the next generation of cosmic structures. By refusing to collapse entirely into a black hole, by maintaining its existence as a neutron star, it preserves its material for eventual recycling. This is the true meaning of persistence in the cosmos. It's not about lasting forever as an individual object. It's about contributing to the eternal cycle of creation, destruction, and recreation that defines the universe. The pulsar spins not for its own sake, but because physics demands it, and in spinning, in pulsing, in slowly releasing its energy over millions of years, it fulfills its role in the cosmic story. As you drift into sleep tonight, floating in that peaceful space between waking and dreaming, carry this thought with you. You are made of stardust. The atoms in your body were forged in the cores of massive stars and scattered into space when those stars died. Some of those atoms may have passed through a neutron star stage, compressed to nuclear density, spun to incredible speeds, and then released back into space through collision or merger. The universe is a great recycling system, endlessly transforming matter and energy from one form to another. Stars live and die. Neutron stars pulse and fade. But the atoms continue, moving from one structure to the next, participating in an endless cosmic dance that has been going on for 13.8 billion years and will continue for billions more. The Crab Pulsar will someday go silent, but the matter it contains will persist, and somewhere, billions of years from now, in a solar system not yet born, around a star not yet formed, those atoms might find themselves in a new configuration, perhaps in a planet, perhaps in an ocean, perhaps in something alive, something conscious, something capable of looking up at the night sky and wondering about the stars. The quiet corner of the universe where our pulsar resides returns to its patience. The nebula around it continues to expand and fade. The background hum of cosmic radiation, that faint echo of the Big Bang, continues uninterrupted. And deep in the cold vacuum of space, the neutron star spins, a little slower each day, but still spinning, still persistent, still defying the darkness with its rhythmic pulse, until the next awakening, until the next story, until the next moment, when matter reorganizes itself into something capable of wonder. The universe will continue its patient work. Stars will be born and die. Galaxies will merge and drift apart. And somewhere, always, a neutron star will be spinning, keeping time, maintaining the cosmic rhythm. Sleep well, dear traveller among the stars. Dream of collapsed suns and spinning magnets, of lighthouse beams crossing the void, of matter compressed beyond imagination, yet still structured, still ordered, still defiantly complex in a universe that tends toward simplicity. Dream of the star that refused to die, and in dreaming, remember that you too are part of this great cosmic persistence. Every atom in your body is billions of years old, forged in stellar furnaces, scattered through space, gathered by gravity into planets, and somehow, miraculously, organized into the complex pattern that is you. You are the universe experiencing itself, a temporary arrangement of ancient atoms that has somehow achieved consciousness, the ability to wonder, to question, to seek understanding. And in that sense, you share something profound with the pulsar. You both persist, at least for a while, maintaining structure and order against the universal tendency toward decay. The neutron star does it through physics, through the interplay of rotation and magnetism, through quantum degeneracy pressure and nuclear forces. You do it through biology, through metabolism and homeostasis, through the countless chemical reactions that sustain life. But you both do it. You both resist entropy, at least temporarily. You both are monuments to complexity in a universe that favors simplicity. And when your time comes to return to the cosmic cycle, as the pulsar's time will eventually come, you'll both contribute your atoms back to the universe, to be used again in future structures, future stories, future moments of wonder. The universe hums eternal and patient, and in that hum, if you listen carefully enough, you can hear the pulse of a distant neutron star, broadcasting its message across thousands of light years and hundreds of years. I am still here. I persist. I endure. And when my time is done, I will return to the cosmos, and something new will be born from what I was. That is the final lesson of the star that refused to die. Persistence isn't about lasting forever. It's about lasting long enough to matter, long enough to contribute, long enough to pass something meaningful to the future. And with that thought, let sleep embrace you completely. The stars will still be there when you wake. The universe will continue its slow, beautiful unfolding. And somewhere, in a nebula 6,500 light-years away, a tiny spinning star will pulse once more, adding its voice to the cosmic chorus. Good night, fellow stardust. Until the next journey through the infinite, the universe whispers, rest now, for you are home among the stars.